I'm excited to be here. The talk you're going to hear today is going to be pretty oceanographic in nature, and the kind of like focus of it is the physical and biophysical mechanisms by which new nitrogen is introduced to the coastal ocean in Southern California. And we're going to talk about two little vignettes, one that is related to something that you guys have probably witnessed or at least are aware of, which is high biomass dinoflagellate red tides. And this is a picture of the bioluminescence generated by a particular one of those organisms, Linglodinium polyhedra. And then the other is going to talk a little bit more generally about nitrate delivery. And of course, nitrate is a primary nutrient for kelp forests. So before I get going much further, I did want to start with this.
This is a weird way to start a Zoom lecture with something pre-recorded. Couldn't figure out how to do this on Zoom, but in honor of the kelp culture lecture series, I wanted to show my bona fides.
Yeah, so it was pretty we don't need to watch that again. It was pretty classic when you guys reached out to me. I was like, oh, these are my people. Anyway, with that introduction aside, let's talk a little bit about nitrogen in the coastal ocean, or nitrogen in the ocean in general. And on the right here, we have kind of a full description of the marine nitrogen cycle. There's a lot of pathways and a lot of sort of details. And I am no chemist. But what we're really kind of going to talk about in this talk is, I presume you can see my cursor. We're going to talk really about kind of two pathways of this kind of amazing and detailed cycle. One is the pathway that this is nitrate here. One is the pathway that brings nitrate into the surface ocean, into the euphotic zone. Also pathways that bring it into the coastal ocean. And another is related to the pathway that brings this inorganic nitrogen and turns it into organic nitrogen, or, takes it from the inorganic pool and puts it into the organic pool, which of course kelp would be one example, phytoplankton, etc. And one of the things that you learn if you take a lot of observations of nitrate in the coastal ocean in Southern California is that on like kind of long time scales, the sources of nitrate and the sinks of nitrate, sources being primarily physical in nature, sinks being primarily biological in nature, are basically balanced. And what that kind of results in is that there's sort of a canonical distribution of nitrate as a function of depth, basically. It's not quite depth, and we're going to get into the details there a little bit. And so that's kind of like a climatological fact. If there's a program called CalCoffee, which has been taking measurements of the physical and biogeochemical state of the ocean off of California for 70 years. And if you look at that as a whole in Southern California, you'll see that there's this really consistent relationship of nitrate versus other ocean properties. And the key kind of thing that we're going to use about that is that it's not quite a relationship with nitrate and depth. It's a little bit more correctly said that there's a relationship between nitrate and temperature and salinity, or nitrate and density. And so another way of putting that is, as you go deeper in the ocean, the density increases, the water gets colder is the main driver for that. And if and if you're kind of in the business of tracking ocean properties, or trying to figure out where the currents are moving property A from location A to location B, what we do is we track those properties on these density surfaces. And the reason for that is that on these, we call these density surface isopycnals. It's just a term of art, but it's basically saying the ocean is a layer cake in the vertical. As you go down, this layer cake has increasing densities. For example, here's a little picture of this is nitrate as measured versus depth on the y-axis and versus time on the x-axis. And you see there's just some squiggly gray lines. And those squiggly gray lines are these density surfaces. As you go from the warm surface to the colder subsurface, the density is increasing in this layer cake. And you can see these squiggly surfaces kind of tend to move together up and down. This movement up and down is related to waves that are propagating through the ocean. We call these internal waves. But they don't actually do much to the density distribution on a time average sense. They're just kind of just like the surface waves that are moving across the surface of the ocean. They're just kind of moving things up and down. And so if we're interested in the changes of properties in the ocean, rather than just sampling on depth, this natural frame of reference is to understand how the properties are changing on these density surfaces. And so everything I'm going to tell you about moving forward today in terms of what we measure in the coastal ocean, what we specifically measure in the coastal ocean, is related to this concept of we're going to be tracking the changes of nitrate on these density surfaces. Just because it gives us a little bit more of like a kind of conservative way of looking at the ocean property changes and a little bit less, we're a little bit less confused by kind of variability associated with wave processes, with tide processes, and with currents. And so you'll get a little bit more experience with that as we move forward. This is a very sort of physical oceanographic kind of perspective, and it may not come naturally to you at first, but hopefully by the end of the talk, you'll understand why we do this. Oh, I should also mention if you've got a burning question, feel free to interrupt. You can raise your hand. I'm sure I'll see you, and you can. I'll stop and you can go ahead and ask any question or if you need some type of clarification. Okay, so the trick to being able to measure these properties on these density surfaces is that you need some way of measuring all of the ocean from the surface all the way to whatever depth you're interested in. And in our lab, we've built a system that does that automatically using ocean waves as the propulsive force. And so here's a cool little stop motion animation that a colleague of mine put together about our platforms called the Wire Walker. And I'll kind of just narrate. And so, we're really interested in understanding the biophysical and biogeochemical variability as a function of these density surfaces. So we build this system. It's pretty simple, actually. There's a surface buoy and there's a bottom weight. It's all under tension. The vehicle rides on the wire. It can either be moored or it can be free drifting. And there's a rectification. There's a mechanical system inside of the vehicle that turns the two-way motion of the surface buoy following the surface waves into one-way motion for the vehicle. And the vehicle is ballasted to float. It's positively buoyant. So the waves push it down kind of with a wave motion. And then once it gets to the bottom, that mechanism is released and it simply floats back up to the surface where the mechanism is re-engaged at the surface and the waves push the vehicle down again. And so by doing this, we're able to create this map of the ocean properties that's got observations at all these different depths. And if it's moored, it can be all the way from the surface to the bottom. And we're able to track that in time. And so this kind of disambiguates the ocean variability in a way that single point measurements can lead to some confusion. So we've been building these systems for, I don't know why videos always do this. Okay, we've been building these systems for a long time. I've been working on this since I was a graduate student, which was a long time ago now. This is a really fun system we put together. This is the Wire Walker in real life. This particular Wire Walker is measuring the physical parameters, so the ocean temperature and salinity, the density field. Something about, or various things about the biological properties via optics. So it's measuring the amount of chlorophyll in the water. It's measuring the amount of turbidity or sort of like cloudiness of the water, measuring how much CDOM, we call it, chromophoric dissolved organic material. It's another optical channel. We measure the amount of light that's available. That's this sensor here or here. And then finally, with this system, we measure the amount of nitrate. So this is a UV spectrophotometer that you buy off the shelf, and we've incorporated into the vehicle, and it is giving us real-time measurements of nitrate. And then we just let this thing loose, and it's profiling from the surface to the bottom. So the first little story I'll tell you here is about a story associated with a really strong red tide that we had throughout the entire Southern California bight, maybe strongest in San Diego. This is a picture looking back at Scripps Pier. Even though this was on the advertisement, this is actually not me. I took this picture. Um, this is my colleague Tyler, and this is right at the beginning of COVID. This is April 2020. So we had to get all sorts of special dispensations to go out there, and that's why he's wearing that silly. That was before we even knew that the like cloth face masks were didn't work. So this is the biggest bloom on record. Scripps has been looking at these blooms for almost 100 years, and this is the biggest red tide that we had on record. Um, it got up to concentrations of 9 million cells per liter, which is a crazy number. It absolutely completely changed the biogeochemistry of the coastal ocean off of San Diego. The pH was almost an order of magnitude different than it normally is. Dissolved oxygen, when this bloom started to decrease, went to zero. We had fish kills. It was just a serious event. And these organisms, this is Linglodinium polyhedra, they're not toxic or basically thought to be non-toxic, but because they reach such high biomass, they can create havoc in the ecosystem, especially when the organisms when the bloom starts to die. And they're a complete monoculture when they're in this kind of modality. So from a planktonic perspective, so typically quite a diverse phytoplankton assemblage in San Diego and Southern California bight in general. And during these conditions, there's nothing else, and we can prove that directly, as you'll see in a second. So this has kind of been known forever. This predates UCLA and UCSD and almost predates the UC system. This is a paper from 1901 or 1902 that was from a 1901 Linglodinium. They used to call it Goniolax, but it's the same organism that caused a fish kill in Long Beach. And the kind of thing that was baffling to everybody about these blooms until this guy came along, Dick Epley, who's a Scripps scientist, was the nitrogen budget did not add up. There was way more phytoplankton than there could be supported by the amount of available nitrogen where the phytoplankton was. And that was a puzzling thing. And they began to do laboratory experiments. And in the laboratory experiments, they note a lot. They noted, so their laboratory experiments are in a deep tank, and they're able to control the day-night cycle. And what they noted in those laboratory experiments is that the organisms were really good at swimming, and specifically in a vertical sense. These dinoflagellates are exceptional vertical migrators. And so the hypothesis was that, like little tiny photocells, they swam up to the surface during the daytime to photosynthesize, and then they were going down at night to the deep inorganic nutrient pool, absorbing the nutrients they need to continue to grow and photosynthesize, and then returning the next day to the surface in order to photosynthesize again. So this is one of these classic science stories where there was a hypothesis advanced 50 years ago. Everybody kind of, takes it as truth. But as it turned out, no one had actually shown the actual connection between the vertical migration of these organisms and the drawdown of inorganic nitrate at depth at night, and the increase of the organisms as a function of this vertical migration. So there's this crazy red tide. It was during COVID. We had built this system up. We had some seed funding, and we built this system up. And so we decided to deploy it. And we leveraged another piece of equipment that's right nearby Scripps, and it's this buoy, which is a long-term installation just offshore of Del Mar, California. And what it has, which is really, really cool, is this thing called the Imaging Flow Cytobot, IFCB. This is a really amazing piece of equipment that does microscopy at the buoy. It's only at one depth, unlike our profiler. So our profiler can measure the bulk properties, how much chlorophyll there is, but it can't tell us what organisms are there. This thing is taking pictures of the organisms, and counting them. So we know exactly what's there, but it's only at one depth. And so what we did was we combined those two things. So here is some microscopic images from the IFCB during this red tide in spring 2020. And there is the picture, excuse me, the line drawing next to it from the 1901 paper. These are 100% the exact same organisms. And it's fun to work on a problem that's been around for so long. The timeline of photos or of microscopy images here. Again, these are collected in situ. This is an automatic system that's working on a buoy, and the main not I mean it's obviously like we didn't make this. This is my colleague at Woods Hole named Heidi Sosek. In addition to the actual building of a system like this and having a microscope that works at sea for prolonged duration, which is not easy, the software side of it, which is processing these images on board and can count how many cells there are and thus give you an idea of the amount of actual sort of numbers and biomass of things, is itself a decade-long investment in this technology. Okay, so if we look at the biomass here, this is over the course of this bloom. This is from the IFCB, so this is cell count, so it's turned into a carbon biomass via what we kind of know as like the average distribution of the cell size versus carbon from these organisms from the laboratory. And we've got biomass, this is micrograms of carbon per liter. The average biomass in micrograms of carbon per liter in Southern California by normal kind of quasi-oligotrophic conditions is down around a couple hundred micrograms per liter. And as you can see here, we were just going way past that. So that's one thing to see. You can see this bloom. The blue line is all plankton of a particular size class. So this is kind of the phytoplankton size class, but smaller than zooplankton. This is specific to phytoplankton here, basically. And then the red line is our red tide forming organism. So the one thing you can see is this massive increase that was really focused around the middle of April, May. The other thing that you can see about this is that it's very, very spiky. And so we're going to talk about that spikiness. I've already kind of given you a hint as to what that spikiness might be related to. I'll give you another one. The gray bars here are nighttime, and the white bars here are daytime. The bottom plot is just the ratio of these two lines to each other. And the ratio of these two lines to each other gives you an idea of the total amount of plankton that's being seen at any one time. What fraction of it is this red tide forming organism? So you can see that it starts off quite low, and then it gets to a point where at times it is almost 100% of what they're seeing with this microscope. But again, we get this sense of these drastic changes over a course of a day or two. Okay, so basically what the surface microscope below the buoy is telling us is that there are a lot of this dinoflagellate. It is dominating the ecosystem during this time. It is at exceptionally high biomass, and it is changing from day to night. So that's all, pretty good evidence for this idea that it's going somewhere. It's not, and I should say this microscope is right at the surface. It's at 3 meters depth. And so there it is at 3 meters depth during the day, and then at night, it's gone. And obviously this is consistent with this vertical migration hypothesis. So this is where our profile, but you can't say much more than that from that particular instrument, right? It's there during the day and it's not there at night, but where did it go? Who knows? So that's where our profiling system comes in. I'm just showing the upper 50 meters. We had it deployed in 100 meters of water. It's going from the surface to 100 meters and back every 10 minutes on average. So 6 times an hour, 120 plus times per day for multiple weeks in a row. So this is constant surveillance, surface to bottom at this mooring location. We've got some of the physical properties, temperature. You can see it's nice and warm near the surface, cold down at depth, salinity, which is how salty the water is. And then this panel E and panel F here, the kind of smoking gun panels. The first is chlorophyll concentration. This is a bulk chlorophyll concentration. We're pretty sure this is linglodinium just because we have this microscope that's showing it at the surface. And the first thing you can notice when you look at chlorophyll in this way is beautiful patterns of high chlorophyll near the surface and then descending over the course of the day. And you see that over and over and over again. And the crucial and critical thing about this is that this chlorophyll is descending and it's crossing these, it's crossing these gray lines. And so physical processes in the ocean happen almost exclusively along those isopycnal surfaces. The currents, the waves may move the surfaces up and down, but the only thing that moves things across those surfaces is physical mixing, turbulence. This is a process that is not physically mediated if it is crossing these lines. So I'm going to show another panel. It is almost exactly the same, except now we're going to be looking at the projection of the chlorophyll and nitrate along these lines. We're going to basically hold these lines steady, these isopycnal surfaces, and imagine that these heaving associated with internal waves was not there. And so that is the picture here. This is the same exact data. I haven't done anything to it outside of I changed the frame of reference from a frame of reference associated with depth to a frame of reference on these isopycnals. And that allows us to separate the vertical variability associated with all the waves and current processes from the biological process of swimming. So here is panel B. It's again chlorophyll as a bulk quantity, and it's projected into kind of a depth-like coordinate, but it's actually flat on isopycnals. And these downward propagating kind of signals are the phytoplankton swimming. They're exceptionally good swimmers. So we measured this. This is in situ measurement. This isn't a laboratory. We're not messing with these organisms at all. We're just observing them in the field. They're moving at about a half a millimeter a second, which doesn't sound very fast until you consider their body size. And that's kind of how most metrics for swimming work in the ocean, at least at high Reynolds numbers. The bigger your body size, the faster your hull speed. They can move at about 10 body lengths per second. The fastest fish in the sea is the short fin mako shark. Excuse me for calling it a fish. It's not a fish technically, but anyways, the short fin mako is extremely fast swimmer, and it moves at about 8.5 body lengths per second. So these guys are moving at a speed that's kind of like pretty crazy. Pretty crazy relative to their body mass. I actually don't fully understand how they do this because they're operating in a viscous environment, and this still seems difficult, but to understand. But anyways, we measured it. Their swimming is quite cool. It is cued by light, their descent phase. So they kind of start swimming downwards, more or less at just around sunset. And the depth of their excursion, these black lines here, is the concentration of inorganic nitrate. And they are, basically swimming down until they detect the fact that there's nitrate above zero, and then they're stopping. And you can see that sense of the depth excursion of this swimming being very tightly coupled to this really strong gradient from zero nitrate up here in the surface to high nitrate at depth. So here's nitrate. And so that's another nice smoking gun. We're seeing their swimming is associated with light. We're able to measure the swimming speed, and we're able to show that their swimming stops where the nutrients, the nitrate specifically, gets high. So there's one more piece to this puzzle, and that is, can we observe how much nitrate they're taking up, and can we relate it to the amount of phytoplankton growth? And so here we've kind of contoured an anomaly. Again, this is on these isopycnal surfaces. And on these isopycnal surfaces, the only two things that can change the concentration of nitrate are one, turbulence and mixing, and two is non-conservative processes like biological uptake. And what we can see is that at the beginning of this, swimming phase, the nitrate is relatively high on this isopycnal here that's centered around 30 meters. And as you move forward in time, that nitrate becomes depleted on that isopycnal. And that is the same isopycnal to which these organisms are swimming. So there's some more details on how we quantified this. If you'd like to read more, this was published in the Proceedings of the National Academy of Sciences a couple of years back now, and we were happy to have it be on the cover of that journal. And we did one more little trick here. In addition to tracking these isopycnals vertical movements up and down, we're also able to track horizontal movements of water due to something that we call spice. And spice is the way that temperature and salinity act together to control density. Temperature, as temperature goes down, the water gets denser, and salinity, as the water gets saltier, the water gets denser. But what that means is that for a particular density class or particular density number, density X, you can have a range of temperature and salinities that add together to make that one particular density. And so it's like a fingerprint of the water's sort of origins. And we're able to vary in a very kind of a detailed way. Here's temperature and salinity as a scatter plot. And this is a temperature and salinities on this line here all make the same density. And so what we're able to do is we're able to track as the water is moving up and down the coast, a particular density surface will have variability in the temperature and salinity on that density surface. And it gives us this sort of fingerprint. And what we were able to do here, or what we were able to show is that we're able to estimate the rate at which nitrogen is being drawn down on these density surfaces as a function or in little bins that are these little temperature and salinity bins. And so the combination, and it's probably a little bit esoteric, and I'm happy to answer questions about it. For a non-oceanography crowd, it's probably a little bit esoteric. But the point is that from this particular single mooring location with full depth coverage, we're able to sort of control for the fact that the ocean is kind of moving up and down internally with internal waves, and it's definitely moving back and forth up and down the coast and back and forth across the coast. And it's inherently patchy. And so that was, basically at the end of the day, controlling for that physical variability is the reason why this hypothesis had kind of been unproven in the field until we were able to make these measurements. So, kind of as a summary of this component of the work, we're basically able to quantify the fact that on these isopycnal surfaces at the bottom of the vertical migration, we're getting an uptake of nitrogen, inorganic nitrogen, that was similar to the measured rate of uptake of inorganic nitrogen of this organism in the laboratory. And the final kind of piece of the puzzle here is in panel B, which is the comparison, a normalized comparison between the uptake of inorganic nitrogen associated with this migration, which is kind of this panel here. That's the blue line. And the integrated amount of chlorophyll and turbidity. These are sort of bulk properties that are related to phytoplankton biomass. This blue line is the loss of inorganic nitrogen due to this biological process, and the red and black lines are the increase of the plankton. And again, this is the increase of the biomass and these bulk properties. And these are proportional to each other given the expected ratios of the amount of nitrogen to the amount of carbon in the cells of these organisms. So this was kind of a, pretty clear demonstration that that this vertical migration was indeed directly linked to the nitrogen drawdown. It did indeed explain the way that these organisms, at least from one perspective, the nitrogen needs of this biomass bloom were satisfied by this biological process. And so I just want to talk briefly about like why this matters in a larger scale thing. I mean, it's a red tide. It's bioluminescent, so it's pretty. That part's cool. It can be pretty stinky and kind of bad for the ecosystem as the bloom starts to decay, as I mentioned earlier. But I wanted to really emphasize this is an incredibly effective way of changing the biogeochemical properties of the coastal ocean that will affect the entire ecosystem. So this is a plot here. I'm just showing the concentration of nitrate as a function of the temperature of the water. This is quite similar to this idea of the nitrate being sort of distributed on these density surfaces. And the purple histograms are the distribution of the nitrate concentration as a function of temperature from measurements that span 69 years from the Cal Coffee program just offshore of us here at Scripps. This is the innermost southernmost Cal Coffee station. This is an incredible record. It doesn't exist really. This type of record doesn't exist anywhere else in the world, so we're very lucky to have it. And it shows that the nitrate increases functionally linearly with temperature until about 14 degrees C climatologically, and then it's zero above that. The green histograms are the observations from our field study during this red tide. And the sort of range between about 11 degrees C and 14 degrees C has a way different distribution of nitrate with temperature. And the nitrate goes to zero at a level that's much colder and thus much deeper than the previous 69 years of data showed. So this is this is a quarterly or less kind of climatology, so it's easy to miss events like this. But the point is that there are no observations over the 69 years that showed such a major perturbation to the background field. And, macrocystis has a high nitrate demand, and these organisms are pushing the nitrocline down to depths that are 35 meters, between 35 and 40 meters deep. That's below the holdfasts of most macrocystis. So these high biomass blooms definitely have an impact on the kelp forest nutrient delivery. So here's another way of looking at it. Here's a reconstruction of nitrate. Here's 0 to 50 meters again in the vertical, and this is about 3 weeks of profiler data. And here I've taken the climatology and made an estimate of what we would expect the nitrate to be based on the climatology. And here I've just showing what we've already showed, which is the measured nitrate during the bloom. And the difference in these two things is in purple here. These are huge deficits. And the nitrocline is 10 meters plus deeper. Here it's going down to 40 meters at times. So that means there's zero nitrate above 40 meters. This is sort of similar to what a really, really strong El Nino does to the nitrocline in terms of depressing it so deep that the macrocystis communities can get starved of inorganic nitrogen. This is much shorter than an El Nino. It's only about 3 weeks in duration, but it has a kind of a similar scale of impact. So there's all sorts of other little tricks that we did. We kind of came up with a total biomass of the bloom as a whole. We kind of tried to understand a little bit more about the sort of. Oh, one final thing I want to say about this particular map is that I mentioned before that the organisms were not only extremely high biomass, but they're basically a monoculture. And the way that they establish that dominance is captured in this map. Because they can vertically migrate, they're able to, kind of get the amount of light that they need to continue growing and the amount of inorganic nutrients they need to continue to grow, even though the nutrient pool is so deep. And that is not the case for the other phytoplankton that are non-motile. So in a situation like this where you've got a nitrocline that's depressed to 30 meters or 40 meters in the Southern California Bight, that's a very low productivity condition for anything that is not capable of being motile itself. And so that includes the sort of primary class of organisms in the kind of phytoplankton, the kind of sort of bigger scale size class phytoplankton, the diatoms. And so there's, diatoms typically dominate around here, at least in San Diego. And there was basically zero during this bloom. And the reason is they just cannot, they're not motile. They cannot access both the amount of nutrients they need and the amount of light they need when the nitrocline is so low or depressed so deep. Okay. Um, I think that rather than kind of blabbing on about this next bit, which is maybe I can come back and talk to you about it, maybe I'll just stop here and we can just start a conversation about this process. And yeah, and if there's no questions, then I can keep talking. But so let's do that. If there's any questions about or you'd like to have discussion about these amazing organisms.